when I was doing my final year IT project, I decided to build a system that would be able to generate timetables for students at my school. So it'd be very simple. Students would enter the classes that they take, English, IT, biology, or whatever other combination they have. And then the system would create a timetable for them. But as I started coding this system, I quickly realized that this problem was way more complicated than I had originally anticipated. Since there are so many different combinations of classes that students could take, and then a certain combination might only exist once or twice. And then you'd also need to consider that certain classes might have one teacher and other classes have four teachers. So there were so many edge cases that this problem really started to seem like it was impossible to solve. And I feel like that's an experience that, as people working in IT, that we can relate to. Eventually, going to come across a problem that really doesn't seem like it has a solution. And if I had known back then about hyper-heuristics, I really think I would have been able to solve the problem and to build the system and have it work as well as I wanted it to. So, but before I can tell you about hyper-heuristics, there are a few things that we need to go over first. So first of all, what is combinatorial optimization? Combinatorial optimization is the process of finding the optimal solution for a problem from a finite set of possible solutions. But what does this really mean? So let's say we have some problem that we'd like to solve. If we decide to use combinatorial optimization to solve the problem, we would do the following. So we would create a bunch of solutions for a problem. They don't have to be good solutions, so it just needs to be within the constraints of the problem. So if the problem that you're trying to solve is adding two numbers together, the solutions that you create would at least need to be numbers. So they can't just be completely random values. And then from those set of solutions that you created, you just select the best one that you have. So to illustrate this, let's sort a list of numbers using combinatorial optimization. So the problem that we're trying to solve is to sort this list of numbers in ascending order, 4, 1, 3, 9. So we're going to randomize this list to create our solutions. So we're going to randomize the list 4 times to create 4 solutions. You could create 16 solutions if you wanted to, but for this example, I'm only going to be creating 4 just to keep it a bit more compact. So we are going to randomize the list to create our first solution, and we get 19143. We randomize the list again to get our second solution, which is 3491. We randomize it again to get our third solution, which is 3914. And we randomize it one more time to get our fourth solution, which is 1349. So now we have our set of solutions for the problem. So now we need to assign each solution that we have an objective value. So we can see in our first list, the numbers 9 and 4 are not in the correct location. So we give an objective value of 2. In our second list, we can see that only the number 1 is not in the correct location. So it has an objective value of 1. And then in our third solution, we can see that the numbers 9 and 1 are not in the correct location. So it has an objective value of 2. And then in our last solution, none of the numbers are in the incorrect location. So it has an objective value of 0. So we can see that from the solutions that we created for the problem, that solution number 4 is the best solution that we have. So we could select, we select solution 4 as our solution for the problem. And this is essentially how combinatorial optimization works. I haven't explained all of the details, but creating solutions for your problem, sometimes even randomly, and then just selecting the best solution that you created is essentially how combinatorial optimization works. But why would we ever want to sort this way? It seems so inefficient. Why don't we just use an algorithm to sort the list of numbers? And we even know that there are algorithms that can sort the list of numbers for us. So it really seems like combinatorial optimization is a complete waste of time if we can just use an algorithm to find the solution immediately instead of creating a bunch of solutions. So this is where problem classes come in. Problems can generally be classified as being polynomial or as being non-deterministic polynomial. I'm sure that most of you have heard of P versus NP at some point. So problems that are classified as polynomial have algorithms that can solve them in polynomial time. All that this means is that if for the problem, there's some algorithm that can give you the optimal solution in a relatively small amount of time. Sourcing a list of numbers is considered a polynomial problem since we can use an algorithm to give us the optimal solution almost immediately. And then you also get non-deterministic polynomial problems. For these sorts of, there's no algorithm that exists that we know of that can just give us the optimal solution immediately. So, and it's for these types of problems that we can use combinatorial optimization. So we use combinatorial optimization to find a good solution for a problem when there's no known algorithm that we can use to just give us the optimal solution immediately. So to illustrate this further, let's solve a well-known non-deterministic polynomial problem, the traveling salesman problem. It's very simple. The salesman would like to visit each of these cities represented by the letters A to E exactly once and start and end at the same city, while also traveling the shortest route that you can. So since the traveling salesman is a non-deterministic polynomial problem, we know that there's no algorithm that can just give us the solution that we want. So let's use combinatorial optimization to find a good solution instead. We aren't going to be constructing the solution randomly like we did when we did our list example. Instead, we're going to be using something called a heuristic. A heuristic is a rule of thumb that you can use to create a solution that you think is going to be better than a solution that you just created randomly. And we're going to be using a heuristic called the nearest neighbor heuristic. It's very simple. We just select the city that's closest to the city that the salesman is currently at. So let's create our solution. So a salesman is going to start at city A, and we can see that the city closest to A is B. So we go from A to B, and then closest to B is C. So we go from B to C, and then closest to C is E. So we go from C to E, and then E to D, and then it goes back to A. And we found our first solution. And this solution has an objective value of 22, which is the total distance that the salesman is going to have to travel. So let's construct one more solution, but we're going to be using a different heuristic. Instead of using the nearest neighbor heuristic, we're going to be using the furthest neighbor heuristic. So it works in a very similar way. Instead of choosing the city that's closest, we're just going to be choosing the city that's the furthest away. So let's use it to construct our second solution. So we're going to start at A again, and we can see the city furthest away from A is D. So we go from A to D. And then furthest away from D is C. So we go from D to C. Furthest away from C is E. So we go to E. And then furthest away from E is B. And then we go back to A from B. And we found our second solution. And this solution has an objective value of 27, which again is the total distance that the salesman would have to travel to visit each city once. So we can see that our first solution is more optimal since it has a low objective value. Our nearest neighbor heuristic found a solution with an objective value of 22, while our furthest neighbor heuristic found a solution with an objective value of 27. So we could select the first solution that we found as our solution for the problem. Or we could continue to construct even more solutions using different heuristics. So when you're using combinatorial optimization to solve a problem, it's a good idea to explore as much of the solution space as possible. The more solutions that you have, the more likely it becomes that you're going to find a solution that's closer to the optimal solution. Well, keep in mind that we don't know what the optimal solution for this type of problem is. So we're effectively just trying to find the best solution that we can. However, constructing a large number of solutions in a way that we just did is very challenging. It's computationally expensive and it's very inefficient. For our traveling salesman example, we only had 5 cities. So it would be pretty easy to explore the entire solution space by just constructing solutions randomly. However, if as the number of cities in a problem increases, it becomes infeasible to explore a large enough amount of the solution space to find a good solution for the problem. So how can we solve this problem so that we can make sure that we explore enough of the solution space to find a good solution when our problems become very complicated? And this is where hyper-heuristics becomes very useful. Hyper-heuristics allows us to abstract away the solution space and work at the heuristic space instead. All that this means is instead of working with solutions directly, we're going to be working with the low-level heuristic that we use to create solutions. So to illustrate this, let's build our own hyper-heuristic to solve our traveling salesman problem. So we're going to be building a type of hyper-heuristic known as selection constructive hyper-heuristic. You also get selection perturbative, generation perturbative, and generation constructive. They do work in slightly different ways, but they all have the same objective of finding the best solution for a problem. So you would typically use a selection constructive hyper-heuristic like we are going to use if you already have a set of low-level heuristics for the problem that you're trying to solve. So, and we already have those heuristics. So the low-level heuristics that we're going to use for our hyper-heuristic is the nearest neighbor heuristic that we know from our example, the furthest neighbor heuristic that we also know from example, and a new heuristic called the middle distance neighbor heuristic. So instead of choosing the city that's closest or furthest away, you're just going to be choosing the city that's sort of in the middle. So our hyper-heuristic is going to explore different combinations of these 3 low-level heuristics that we have in search of the optimal solution. For our implementation, the hyper-heuristic is just going to be selecting these low-level heuristics randomly when it's creating heuristic combinations. But if you were to really implement a hyper-heuristic, you would typically do this in a more sophisticated method, like a genetic algorithm or something else. You wouldn't just select them randomly. So let's say our hyper-heuristic is now complete and it finds a solution. One example of a heuristic combination that a hyper-heuristic might find is the following. So it uses middle neighbor first, then uses nearest neighbor, nearest neighbor, nearest neighbor, and then for the last step, it uses furthest neighbor. So let's apply this solution that our hyper-heuristic found to our traveling salesman problem and see how well it performs. So here's our problem again. We can see that A to D is closest, A to D is furthest away. So for our middle distance neighbor heuristic, we should go A to E, and then we need to go nearest neighbor. So we go E to D, nearest neighbor again, D to C, and then we select nearest neighbor one more time, so C to B, and then we choose the furthest neighbor, which is A. So our hyper-heuristic has found another solution for our problem, and this solution has an objective value of only 21. So we can see that our hyper-heuristic managed to find a solution that's more optimal than the solutions that we found by just using nearest neighbor, furthest neighbor. Nearest neighbor, the solution found near was 22. The solution found using furthest neighbor was 27. And then our hyper-heuristic managed to find a solution with an objective value of just 21. So we can see that it was effective in providing a good solution for our problem. And the really great thing about hyper-heuristics is that we can even reuse this hyper-heuristic that we have for other non-deterministic polynomial problems. All that we need to do is we need to swap out those low-level heuristics that we use that are specific to the traveling salesman problem, like nearest neighbor or furthest neighbor. And we would need to replace those with low-level heuristics that are specific to the type of problem that we're trying to solve. So an example of the type of problem that we could solve using a hyper-heuristic is to construct timetables. So a hyper-heuristic would use low-level heuristics that are specific to timetable construction, so graph coloring or a different low-level heuristic that you want to use. And then it would create heuristic combinations from those level heuristics, and then we could apply that combination to our problem and construct a timetable. And then we could evaluate how good a timetable is using the amount of time that's in between classes or some other metric to decide how good a timetable is. Another sort of problem is optimizing coverage. So let's say you have a very large factory and you would like to have Wi-Fi access at every point in this factory, but you'd also like to use the fewest number of Wi-Fi routers that you can. So we could use a hyper-heuristic to find out where we can place our Wi-Fi routers so that we can get the maximum amount of coverage possible from as few a number of Wi-Fi routers as we can. Another problem that we could solve is vehicle routing. So let's say we have a distribution center and vehicles leave this distribution center to make a delivery, and then they have to come back again. We can use a hyper-heuristic to find routes that are the shortest, that use the least amount of fuel and time. So to optimize the routes that vehicles will have to travel. And then also almost any other problem that involves some amount of optimization, where you can't just use an algorithm to just give you the best solution immediately, where you're going to have to just try and find a good solution. So for any problem like that, hyper-heuristics is very, very useful. So I hope you have a better understanding of what hyper-heuristics is, how they work, and why they might be useful for you to use at some point. I hope you enjoyed the presentation.